So this problem can be a little challenging, but it's actually relatively straightforward if you take care to get a good visualization and assign your directions well. So here we have, in the new movie Tomb Raider, Lara Croft is rescued from the raging rapids of the Tigris River by grabbing onto a rope dangling from a helicopter. She's so determined to hold on to the rope that she lets go of her backpack when she is 160 meters above the water. If the backpack hits the water 7.2 seconds later, what was the speed at which the helicopter was ascending? So we know the helicopter is ascending in this. So we're going to draw that motion diagram of that backpack. So she starts, say, here, and she's going up. So the backpack will continue to go upward for a little bit, decelerating on the way up, and then it will come down, accelerating on the way down, and we'll say that that's where the water is, right there. Traveling up at first, then traveling down here. As it goes down. So this is where our time equals 0, time initial. This is our time final. It's one continuous acceleration. I'm going to call the water is y final, and that's 0 meters. So this is my y initial, and it's 160 meters up, and that equals 160 meters. The accelerations we're in this entire phase from beginning to end is g, 9.8 meters per second squared down. Even though at the peak here, the backpack will hit an instantaneous velocity of 0 meters per second in the y direction, but that's not necessary to figure out what's going on. We know that what we want to find out is how fast it was going right here. What's v initial here? V final here, we don't know that. And time, though, we do know, right? The time final is 7.2. We have that. We have the final position. All right, I think we're good. It's one object, one acceleration, so we can do one list. The velocity initial of this backpack is what we want to find. The velocity final, and these are in y directions, is unknown, and we don't want to know. The y initial, so I called y initial 160. Since we have positive as being up as our convention, this position being higher has to be a greater number, more positive than the lower position. That's 160 meters. Y final is 0 meters. The acceleration during this is g, which is 9.8 meters per second squared down. This is above 0. Down is going to be negative, so I can make that a negative. The time, the change in time between the beginning and the ending, between the release and the landing, is 7.2 seconds. So we look through that, and we see that we don't know the final velocity, so we're going to use, and don't want it, we'll use an equation that doesn't require that. And that is y final will equal y initial plus vy initial, or v initial y, times the change in time, plus 1/2 the acceleration in the y direction times the change in time squared. So we're going to plug in all our numbers there and see what we got. Y final is 0. Y initial is a positive 160. The velocity initial is what we're looking for. The time is 7.2 seconds. 1/2. The acceleration is negative 9.8 meters per second squared. And the time again is 7.2, and this time we square it over there. All right, looks pretty simple. We just need to do some algebra to solve that problem. And the physics is pretty much done. All right. So my calculator has a lovely ability to solve this the way it's written, so I'm going to use that. Plug that all in. And boom, I get 13.05. So that velocity should work out to be 13.05, and it's positive, so it's up, and that makes sense. It should be positive, that velocity in the y direction. 13.06 meters per second. There's actually 2 significant digits, so Vy is equal to 13 meters per second, and that is up. So the algebra here, if you need to go over that, well, that's another class, but you would, add the subtraction 160 over there. This would get added to the other side, combine those, divide by the 7.2. You get 13.06. There you go. Hope that was helpful.